Okay, so let me start. The topic of today's talk would be algebraic geometry in its complexionality. And the model treated as AKSZ field. So, on the first half, I'll explain briefly this, and on the second half, I'll explain B models. So something of this I already explained another day, but I'll repeat. Suppose we have X, smooth manifold. And suppose it is even dimensional. Classical structure is the following data. U cover, U alpha, cover of X. With term subspace O H inside C infinity of U alpha of would be holomorphic functions. Such that first transition function from U alpha to U beta is also holomorphic. And second, there are functions Z alpha on U alpha that form coordinate system. They are holomorphic functions. Coordinate on U alpha. And this is holomorphic function. Okay, so I just want to say that it is a classical complex structure. How do we describe? Okay, classical description. Suppose we already have holomorphic function with coordinates z. Consider an operator. So let me rewrite it in coordinates. I want to be very manifest. No summation over there. So I want to have such globally defined operator that locally in coordinates has this form. So what is the meaning of this mu? Mu belongs to 0, 1 forms because of this object with values in T1, 0 because of this. And if we use such mu, then alt z is not holomorphic anymore. In particular, for example, for constant mu z nu would be, so it's possible to see what should I write down here. Z probably plus mu z. Okay, so this is all. So when I apply, probably with the minus sign, it doesn't really matter. So when I apply this operator here, I will get 0 up to mu squared n. It was an example. In this way, I change complex structure. Now, let me call this iterator B bar mu. Unfortunately, there is no good system to write it down. Okay, I will write it. Because mu sometimes denotes coordinate system. So I write it like this, in the square bracket. Now, I have a condition. Before I have condition, I would like to say what are the O, H, mu. I would like to define them as a kernel of the operator B bar mu acting on infinity function. Now, O, H, Q is big enough, and in particular it contains holomorphic coordinates if this operator squares to 0. If it doesn't square to 0, we have so-called Fredholm abstraction. We have consequences of differential equations. You see this? These are differential equations. So when we commute them, we have consequences. And we don't have these consequences. That's why we impose such condition. And this equation, so these equations look like this. And they are known as Kodaira's transfer equations. So what do I mean here? Mu is a 0-1 differential with values in 1-0 form. And I apply d bar. Totally I get 0-2 differential with values in 1-0 form. Now, here I have some bracket. What does this bracket mean? Each mu belongs to T10. So I can take bracket on this T10. And this is the meaning of this bracket. At the same time, mu is 0-1 form. That's why I have 0-2 form. So I kind of explain the meaning of this equation. Now, this is the story about classical complex structure. Because classical complex structure was based on covering of the space by U alphas. However, there is a generalized complex structure in the sense of Barannikov-Kontsevich. Interestingly, it is this complex structure, generalized complex structure, that appears in the B model.
Excuse me. There's d bar mu bar. Why there's an extra mu bar over mu?
Sorry. No mu bar, it's history. In the generalized complex structure, we do the following. We say that mu belongs to omega dot, zero dot times polyvector. You may call it U tilde. So element of U tilde is I bar 1, I bar k, j1, jl. And generalized their Spence equation is just the same. And here I just put BV bracket. And it is interesting that we will meet exactly this equation in AKSZ formulation. B model. Now the next object that I would like to tell you would be sheaf, actually coherent sheaf. So coherent sheaf, for simplicity, is the complex of holomorphic vector bundles. Now, how to understand holomorphic vector bundles from the complex analytical point of view. Suppose we have a manifold X. And we have a vector bundle V. And V would be smooth vector bundle. We would like to make out of it vector bundle with holomorphic in this sense. Transition functions. So what does it mean? It means that on U alpha, we want to find sections S alpha how to draw it. Such that on the intersection transition function are convergent. There is a standard way to do this. Pick up a connection. V. And then we call it A symbolically. Rigorously, I need to take, I call it nabla. And let me say that S alpha are such that nabla 0, 1 on S alpha equal to 0. So locally, this nabla looks like this bar plus a bar. And I'll put 0. I definitely have an ambiguity in solving this equation. In particular, ambiguity here is I already used you. Okay, use small. Such that this is matrix value holomorphic function. So at least it is true for line bundle. For non-line, at least it is true for line bundles. For non-line bundle, I have an extra condition. Okay, let us consider line bundle. Line bundle means that complex dimension of V equals to 1. Then it is definitely true. Okay, that's how I am picking up the basis as alpha on a vector bundle with the help of such connection. Probably here I need to multiply from another side. Such that it would work for vector bundle too. So, this object is a complex structure on a smooth bundle. Now I need to check if I have enough solutions. And once again, I need to do the following. I need to take this square. So this is known as F02. And if this F02 is non-zero, I have extra conditions. And they could not form a basis with holomorphic transition function. That's why my condition is this one. You may observe similarity between these equations. And then I would like to do the last thing. And the last thing that I'd like to do is to introduce complexes. suppose I have not only one vector bundle, but several vector bundles. Then complexes of vector bundles would appear in the following way. E dot now are vector bundles. And I assume that there is a differential that I'll call delta. That squares to 0. Would I like to put it in the Z grading form? And here is the differential. And this is basically what the sheaf is all about. Okay. Now, let me try to find all the structures. Now, let me tell you what B model is from the AKSZ point of view. And let me try to find all the structures that came from algebraic geometry in AKSZ. So that's what I'm starting to do now. First thing, AKSZ is PT sigma mapped to, so I'll consider dimension of sigma equal to 2. To PT star, and now the equation is of what? And here it would be PT 0, 1 of x. So I need to explain what kind of coordinates do I have here. I have coordinates from this x. I have coordinates x. Holomorphic coordinate. I have anti-holomorphic coordinate. I have PT star to them. So this would be, would I have only complex manifold X here? But I actually have more. I have PT01. So it means that I have extra coordinate Pi bar with the bar. Coordinates in the fiber here. Probably since I have shift in parity, it's better to call it not P but pi. And of course I have anti-field. And since I'm mapping PT sigma here, my fields would be all of these with the heads. Okay.
Could you repeat this? What do you mean by heads?
So first of all, I would like to change notation a little bit. I'm sorry. It's better to call them size. So it was last time. With the head, it means that they are form of indefinite degree.
So you mean that, for example, x hat contains all degrees of
Yes, x hat contains all degree. Yes, because I am mapping T sigma. Okay, and now my goal is to write down the AKSZ action. And surprisingly, the AKSZ action is relatively simple. Here I use holomorphic indices only. And here I'm using important thing. Here I will implement Dalbo differential through BV language. I want to put all indices properly. So you may ask the question, why it is not a canonical BV action? Because not a canonical AKSZ. Canonical AKSZ, remark, contains multiple terms contains also. It is because these terms could be removed with the help of this piece. Actually, this term is, so let me call this term SC. So difference between canonical and simple form, or delta SC. So delta SC is S minimal. Let me call this S minimal. And here it is easy to know what to write. I need to write psi bar I star 1 second. Let me try to find. So I want to generate this term out of the commutator of this term. I think it is this one. So if I commute psi bar x bar star with this term, I will have x star dx and psi bar d psi star. So this is exact contribution. And in the minimal form, I may ignore it. Okay. And now I'm ready to study deformation. So what is deformation? It is the function of all fields. Etc. Psi star and actually if I will look at deformation, I will see the following. I will see differential forms of this type. And also I would see fields depending on x star. So functions of x bar, psi bar, and also x star are exactly objects that appear in the generalized complex structure. Now, last time we discussed boundaries of the modular space. Suppose we have a modular space of points on a sphere. And I'll come to the disk a bit later. So on the sphere, I have the following thing. I have a field, F, and I have this differential that I expand from the action. And I consider this boundary. And what I'll definitely get here, I'll get d bar f. But there will be also terms where f go around each other. And when f go around each other, it will be exactly like in AKSZ theory. And in this way, we reproduce generalized equation, generalized Kadeira-Spencer equation for generalized deformation of Barannikov-Kontsevich. Okay, now we need to make a break. Yes, and we start, as always, at 16:30.
一个 F， 它画这个图，是对，上节可以讲到两个这张图，但是说有一个什么 polyback 这个方案这种 sphere， 转一圈会有一个，对，转讲了一个，先从这个球开始讲，然后讲了一些 disk 和 Kontsevich， 可以在边界上也放一些啊，然后这个好像是一个球的。球正常放一个我不知道，但是我觉得他说这个应该有这个上面这些是他说系统会不会是 OFUF 记住这个图啊？上次那个图是叫这个对是有点刚刚嘴巴里面说了，说这个东西就是我们上次说的这个东西。这看再讲这个东西，我们怎么来说？我们上次讲modular space 而且它那个图两个地方，一个地方放了一个 F， 或者它一个是 F， 上面应该是另一个 F 转在那边转一圈，一个 F， 另一个 F 再转一圈，不知道是什么意思。哦，有点像现在什么 vertex 的这种，我们考过我这个 series vertex 转，然后会这样。我不知道，但是这个图看着有点像。它前面解释的也是有点解释的也是有东西在另一个转一圈 ，come around。但是我不知道你说什么东西。他上次也知道，然后是这个。这样的东西，它产生的 can move observer free。就这个里面，你 observer 可以随便走，没有顺序，在这个下面 disk 上 boundary 它意味着它有 order。对，现在这个东西，这个图是在说 correlator。对，说两个 operator 你发现两个 operator。像这里我感觉他只是想说。然后一个转一圈，意思是 correlator 是不变的。对，就是你把两个是互换一下，不变。这里
然后问一下我，但他最后得到了一个方程，就通过那个 master equation，
这个方程是简单的，还是从什
就
么
master equation， 就那个 master classic master equation， 因为你希望你的 theory deform 后，就加上这个 f 这一项结构，因为它跟它这个 master equation， 然后再运算一下，在原来的语言里面的 B model 里面的 x 定义出来的这个 operator， 定义出来这个 operator 就相当于这个，对吧？所以你算出来，本来算出来就是有一些这一项。
没有说 classic master equation， 他说这个东西是怎么出现的呢？这个
他通过这个图这边得出来的。
对，他们就图得出来，然后说这个东西这个 f 就会 recover， 就会满足右边那个 generalized 的 corollary density。
对。
但是他是直接通过这个图。
对，所以我感觉这个图跟这个图。
这个对 f 它这个对象是个什么东西 ？f 是一个场，在 sigma 上面的一个场。这个 sigma 就是个球面。f 上面是 f 是
f 是个函数。
f 它当然不是那种东西，是那个像 d 加 a 的平方这种东西。f 等于2，它是一个 two form。
这个 f 和那个 f 不是一个。
好，这里的这个其实下面和缪巴应该是文form，也不是文form，是 generalized 那种，对，它是一个可能是零星号的 form， 这个缪巴就是这种。
我这个 f 不是方形的，它是那些 field x 八在把 x 标的方形。
但是它这个 x percent 这些东西都是有那个 sigma 上面定义的，但是 t sigma 引过去，所以它都是一些 form 往 sigma。
对。
所以那些 form 往 sigma 是不是就往那个引起的 sigma？ 这没有就是这个。这没有把。
但是一旦单数 f 不它可能是一些方形。
你把它叫方形，但你把它定义在切空间上的方形，是不是就是这个长？就是这个 form， 你切空间的方形。你直接拍入 x 和 x 的 height， 这个 x 八这些东西都是不是这些 x height 这些都是有那个 sigma 组成。
f 脱离了这些 x 八这个根本
没有，我没脱离，我觉得这些 x 八这些对象，这些东西都是 form， 都是 form 型。
对 ，f 坐在上面，它可以最后你要求它是一个修 form。
f 要求它是一个，我也不知道是一个 form， 但它
弯 form。
f 是我弯 form，
弯 form 才能在 sigma 上积分。
你要 f 要积分，
他没有写，你最后肯定是要提这个东西。
哦，就是你要，就是这个 deform 那个 action 里面两个加起来，最后那个第三项的 deform 也是有一个积分 c。你想说的是，这个就是这个，
对，
然后你这个地方其实它漏了一个积分在这里，
对，
所以它应该是文。 但是它我们 form 这边又是个 zero 积分，还有点不一样。
这是 F
sigma 上层积分的 form 一定是我们的 form。
你肯定是要通 sigma 是2维的。
那和那边的 zero 积分不太一样。还说什么？就是这里又有3个 epsilon， 有3个 vector bundle， 它用过这3个 vector。
那3个 epsilon。
那它这里不是有3个 vector bundle， 一个 complex of vector。
这一块我就不知道它在说什么。
对，但是它这里面好像没有什么 vector bundle。
对，它后面那个就是 C。
那总之这个 vector bundle 跑到这个 AKSZ。
他的意思是想说，在苹果的里面，一般你通过那个master equation可以给一个 bold operator， 它 Q， 我们一般把它叫做 super symmetry， 然后 Q square 0，然后你在如果你在英文里面加上15分9的一项，就是后面的那一项 default 那一项，这个 Q 就是一个 generalized complex function。然后在那一项里面，这个 mu 对应的那个 complex function 对应的 function 跟 mu 是一样的，实际上是一个 point vector。
对，代数上来说很简单，就代数上就是这个 s bracket 一个东西，就是一个 differential， 然后它 deform 一下，要还是一个 differential， 它就需要那个 potential 像有一个满足这种条件一样，就是这种非常简单，它说一通。
然后再问一下，我觉得从他那个讲那个什么奇怪，那个 collection 01是什么
？connection 01就那边它是这个意思，说是现在你有一个 vector bundle， 然后你可以在上面自定义一个 connection， 你先取一个 connection 可以取，
对，
你先取一个 connection，
对，
然后我开始解这个方程，去把这个 section 解出来。你想要把这个 section 能够足够多，那目标就是我们要取到一个整体的一个坐标系，可以把它平坦，可以把它那个写成一个trivial， 把它写成那种有足够多的那种section， 有足够多的 solution 的那个一次方程。那么就需要满足这个无举，这个F 是零的，就是基本上没有取对这个条件，没有取对它平坦的，那你就可以找到足够的这个 section， 好像是这个意思。pick up
看那个题，他说他定义出来这个 collection 01它是 vector bundle 上的 complex function。
哦，那他就把这个当做一个differential。
对，但是 differential 是 x 在上 x 在你 space。differential
x 在 section。
对，但你 section 不是你 vector bundle 上的方形。
section 是你空间打到
对，它不是
fiber 的一个 function。
对，但它不是一个 C50 bundle 这种。
什么说？这个 function 是这个 function 就是它的 function 的一个推广。
就我的理解，它要定义某一个，它定义某一个 space 上，它定义 x 上的 complex structure， 上头定义出来一个这样的 operator， 然后找它的写，它的写就是 coordinates。对，
就是你说对函数求导一样的。
对，但
这些就是对 section 求导。
但这个东西它这个 x 上这个 C50 x 上，现在我把 x promote 到 bundle 上，这个东西应该也 promote 到 C50 bundle 上。
不，它这个应该是这样，是 你这个他把是把这个 function 的概念，就这个是个 function x 对，他把这个概念提升到 x 到就 v 本身是一个 x 的一个方面。这是一个 section， 它对 section 求导
它是这种
对，对，你就把 x 到 r 当的一个最频繁的那种那当做例子，你就把每一个 fiber 都想成一个 r， 是这种平板的那种。对，那这种函数就是一个整体平凡的一个来当做的一个section， 第一个函数就意思，但是它就可能整体不平凡的那种那它就来说可能用那个 connection 来代替普通的求导，所以这个正函这个类比较直观，它这个 d 它这个 0 1。就有点像，它的意思就是这个 nebula 有点像 D8， 有点像是对底盘间上的 CR 那个方球。
对，
你一般那个 holomorphic function 你可以看成是体现一个底空一个 base 是一个复列形，上面有 CC8 这种坐标，然后上面 fiber 是一个 R， 每个 fiber 都是 R， 所以你一个 section 就可以看成一个函数，这是 holomorphic function， 用这种刚才的观点来看，有 section 的，所以它现在如果一般的一个 section， 那上面这个D8这个操作就变成了一个类似于 D8的一个求导操作，这个求导操作就是这个 nebula 01这个操作，然后局部上看上去就是D8，但是它意思是 D8可以再多一点，加一点东西。
nebula 01和nebula有什么关系？
它就是那个，但是他想强调的就是他是在对类似于这 C8这个做个求，
01是想强调它是个
对，这个强调它是一个对，它应该是 zero form， 它求导是 zero form， 对
clash，
它应该就是无 form， 它现在就是个 zero form，
一般来说 clash 不是个 form，
它是个 one form， 它不是 connection 你可以吃掉一个向量场，吃一个向量场。然后你可以吐一个向量场，所以它是个向量式的一个 form。它现在相当于吃一个类似于 DC，
但是 one form 是吃一个向量场，给一个向量，给一个常数，
没有，它 connection 是 vector value 的 one form。它吃一个向量场，所以是 one form。刚才说的这块，一个 vector 方法突然到了一个 complex 的 vector 方法，这个他说是就 coherent shift， 也有一大堆 vector 方法，再通过这种 differential 形成了一个 complex。他现在意思就是说，我现在还是保持每一个 epsilon 1、epsilon 2这些分次，但是我 deform 这个不变它，deform 这个。这个 differential， 哎，你说，他这个带去几个流程，他不是自己很想说带去几个，
负分析的代码是那个，他只是在想怎么写这个国的这个系统。
什么叫比？
比方呢，就是这个 action， 这个 action，
所以他的意思是，他的这些背景完全代替了
不是，可能这是符几何作为一个例子，就是能带几何更认识更广，但是这个它形成了一个 complex of 各个方面，可能形成一个假的那种代替。So here mu seems to be a zero sum form, but
mu
here
is not zero.
mu variance, you write it like a 0 dot form.
0 dot, yes.
Yes, okay. And yes,
So d bar acts in this space. So here I have 1, here I have 2.
but here it seems this f should be a 1-1 form because
Why?
we want to integrate it over sigma. We want it to be a top form.
No, we are not. This is observable. This is that we put at a point.
So f is not this deformation term.
The formation term appears in the following way. We take an integral, and here we put f. Okay? And we integrate it over sigma. So we extract differential form out of these fields. In particular, if we have mu that depends on x bar, and psi bar, we need to put hat here. We need to extract 2 form, and we are getting it by using these heads. In particular, when we studied last time, what we studied? We studied deformation with the head. So what this term meant? We had to expand all terms in differential forms. And similarly, the second term. And then I need also to take the following term and so on. But let me explain what it means for constant pi. So for constant pi, that's all. I need to take into account this term and this term, this term, this term, and this term and this term. Because they form a 2 form that could be integrated over sigma. And I can also write the next line. And in the next line, I say that x is x naught plus x1 plus x2. And I can expand indeed. So that's why here I have x naught. X naught has no head. K. And here I write what do I want here? X1, K, plus X2, K, and all this multiplied by this gadget. So I need to take one form out of here, one form out of here, and 0 form out of here. That's how these things are going.
So can I say F here is a two form?
F is not a two form yet. F is an undetermined form. How can you say that F is a two form? So F being function of x bar, psi bar, and x star, you see, all these have heads. That's why this F contains many components, just as I explained.
But this equation is for you get an equation like d bar f.
Yes. So this equation is not for the two form on the source. Let me comment on this equation. I have a theory that has a deformation. And let me further deform by some F. So what happens if I do this deformation? I am integrating over configuration space. I take this down. Okay, plus etc. In the original setting, sigma has no boundary. So this term contains no boundary, I have nothing to worry about. However, this term actually has a boundary, because the first point should be sigma 1 belongs to sigma, and sigma 2 belongs to sigma. And these points, sigma 1 and sigma 2, could come together. And when they come together, I have a problem because of the Green's function. So how do I understand this problem? Suppose that sigma 1 goes to sigma 2. but let me denote this point as sigma 2. And here is the boundary. So this is sigma. Later on, this sigma 2 would go all over sigma, but it's not that fact that bothers me. What bothers me is the region where sigma 1 and sigma 2 are close together. So one can show that green function between sigma 1 and sigma 2 goes, roughly speaking, like, depending on the gauge, the angle of sigma 2 minus sigma 1. So when point sigma 1 goes around point sigma 2, I will get a dangerous contribution. And that is this term that I try to avoid. Now, in the setup of the previous discussion, so I don't want to write down too many terms. I don't want to, okay, well, let me. Suppose I had a field pi that was dependent on the field x, and I put it at point sigma 1. Suppose I have another field, ijkl, at point sigma 2. So what is the correlation function between these fields that could lead to singularity? It could be this correlation function. And what could be this correlation? I don't want to write all terms, but you may easily check that it is pi pi. And here we have Poisson bracket. More generally, if I have pulley vector 1 with indices I1, I and 1, at point sigma 1. And if I have pulley vector 2 with indices J1, J and 2, X star, J1, X star, J and 2, I may ask, what would provide me the green function? Take X star here and contract it with pulley vector 2, or take X star here and provide it and contract it with X. Just two types of terms. And these terms go into BV brackets. Okay, so this anomaly term, this boundary term comes from the BV bracket between polyvectors. Now, let us have a look at this formula. What is important to note here is that this is actually a vector field. On this space. Because it takes X and makes X bar and makes psi bar out of it. This vector field is it's a vector field. That's why this formula should not be that surprising. First term is a bracket between the vector field del bar and polyvector F, and the next term is FF. Or you can even write it as where del bar is understood as a vector field on P01 to X. I'm trying to see what should be explained. Probably this should be explained. It is a property of correlator P and X when we impose condition V star P equal to 0. How to explain it? Consider X as a 0 form and P is the 1. In particular, V star P equals to 0 means that P is V star of some Q. So that's why this object is V star Q VH, or just Q Laplacian X. It means that correlator between X between Q at point sigma X at 0 equal, as we know it, logarithm moduli sigma. But we need not correlator of Q. We need correlator of D star Q. To get correlator of D star Q, we apply D star. Gives exactly this formula. Because it is DZ, делать от Z. So I have this D of angle. Okay. All that means that I can just outline a story about bundles because it's a long story. And I'll come to the story in more detail in next class. the story would be about configuration spaces and boundaries. I would like to do the following. I would like to go from sphere to a disk, as we did last time. So last time we did the following. We had functions everywhere. Now I'll do the following trick. I will take extra vector space. W. And then to each point on a boundary, I associate endomorphism of W Remember that our construction was PT star of 1. So these elements would be F tilde I. And I will define new object. In the following way. Each Fi could be decomposed into basis of this endomorphism of W that I will call EL. So new object would be And here I take a product of these generators. And this would be new correlators. And then let me just announce what kind of correlators would I get and what kind of properties would they have. And I'll explain it in more detail next time. Maybe I do it. The most important object would be the following. If I take F1 alpha to be equal to where this is some matrix. Matrix means with tilde. That depends on x and x bar. And this is how we meet connection that appears in the description of the holomorphic vector bundles. Now, let me tell you where could we meet the flatness condition. That condition, b bar plus a bar equals f02 equals 0. On the configuration space, there are several boundaries. One boundary is a boundary of this type. Where 2 points meet together. And this is a bar square. Yeah. But also there is an extra term. And this extra term goes like this. Here we have this vector field associated to Dalbo. Here we have only one insertion of a bar. And if we look at the Green's function, here it goes this way. And the installation of these two terms leads to equation for holomorphic vector bundle. And that is case number 1. also an interesting case number 2.
Sorry. What is E alpha?
E alpha is a basis.
Basis. What is the
Yes.
And so, in the first case, it should be F1 theta equals to the F1 alpha.
So here I defined object with f tildes in terms of f without indices. So this is a function.
Yeah.
So here we have correlation of functions.
Yeah.
And we know it. And this is a definition of f's with tildes. Okay. So here I wrote it as a matrix. Yes. So it's better to write it this way. F1 tilde yeah, so there's this case, and this case, and together they form this equation of holomorphic values. But there is also another interesting case. Another interesting case is what happens if we consider f be just a function on y, on x. So y is pt01 for x. Then we have the following boundary terms. We have a boundary term. That I will draw like this. It just means that function goes to the boundary. However, this could be cancelled by in the following way. If I take f alpha being equal some function, some matrix valued function of x only, I don't know, probably I should call it b. Then I can have the consideration of the following form. So f alpha tilde equals b tilde equals b alpha x, b alpha. These two terms could cancel each other. And this is called matrix factorization. So next time I will tell you about what I just outlined in more detail. Yes.
which is only a function. So
Yes, so it is, so equation is f times 1 is b tilde square. So you take a matrix that has f on diagonal. Etc. And you decompose it to this form.
what is B here? The second contribution.
B is some special function that I put on the boundary. But it is a matrix. So B is a matrix. So if you look at this equation, it is equation for the matrix.
So in the first contributions, those B's lives in the bulk.
No, here there is no B. Here there is B. So what does it mean? It means that when I'm making deformation with the help of F, I should simultaneously make a deformation with the help of B to cancel boundary term.
Okay, so previously, in the bulk modular space integration, we don't have such insertion B. But but when we consider the boundary of modular space integration, and we put observable F outside, I mean,
On the boundary.
on the boundary, yeah, then we should.
So it should be written in the following over disk. And here we have observable F. And we simultaneously put observable B on the boundary. And we put here deformation parameter epsilon square and put here deformation parameter epsilon. So in the first order, so in the order of epsilon square, it goes as F on the boundary of the disk plus epsilon squared, and here there are B and P. And these two terms cancel.
Okay, so you mean there are two boundary modular space? There are two kind of boundary. One kind is the bulk point goes to
The boundary.
Another case is two boundary points move together.
Meet together. But I need to consider them simultaneously to cancel, to have a cancellation.
We expect to have this cancellation because this form is closed.
We expect because this picture and this picture gives the same for the rest of the disk. And we may hope to cancel this by this.
We hope to cancel because we are doing something like integration, integrate closed form.
No, it's because we want to have this cancellation. We need F times 1 to be equal B tilde square.
So we want to explain this.
We know
further.
if we impose this,
Mhm.
we will have a cancellation.
I see. But this doesn't imply that the form we integrate is a closed form. Because,
It has nothing to do with the closeness.
yeah, because for me, it's like if we integrate a closed form, then it will.
No, it's not. It's not because of the closed form. It is because interaction SBV on F is not zero in general. It is df. So that's why integral over this of F is actually integral over this of df, and this is integral over the boundary of the disk of F. It is explanation of this boundary term. People sometimes write it like this. So point comes from the inside to the boundary. And here is BB term that comes where two B terms collide.
I mean, if we have originally we have a theory, then we can always impose such pair F and V to them.
If we have a function f and we solve this equation, we can cancel the boundary anomaly. If we just put B term, then there will be anomaly because B square is not zero. In particular, that's the way how we are getting to complexes. So I explained something about vector bundles, but how we are going to complexes. We have theories for vector bundles, and we have B term. Suppose there is no F term. Then we have condition that B tilde square equals to this. It means that we have a complex. That's how we are getting sheaves in the B model. Because this term is actually without function f. This term is about complexes. So I should say it before. So there are several ways how points could collide. If points collide on the boundary, we are checking if we have a complex. Or if it's observable of the very special type, namely of this type, we are checking if we have a holomorphic connection. Actually, we will have both. But in a very special case, when we also have F term, we will have something more interesting than a complex. Its solution to equation B square equals to F times 1. Okay, that's the end for today. Sim, when are we meeting tomorrow?
So we are planning to meet afterwards. So I can meet anytime. So if we choose a time that will convenient.
Luis, when are we planning to meet tomorrow?
I don't know.
Okay, but Bowen, I need to take you and to go with me to finance.
No,
Maybe now it's too late.
too late. So they're just still at work. So
Okay.
就是这几张吧。
我能帮我把这个钱拿过去吗？
你现在跟他说过。
这个图啊，有点抽象，就是你上这个，就是首先它可以做一个那种correlator， 它是用怎么做呢？就是用一种这种定义方法，好像是用这种我猜想，就是它现在有两种东西，一种是用一个 action 写出来这种东西，它可以用 action， 然后
一般自己也方法，
哦，你自己拿去了？
我自己拿，他就5分钟后再帮我看。
一般是这样。
它有一个
等下午
有一个像 SIMIS 的这样两个 action， 这是一个不对。
一般可能是1个半小时到2小时。
2点到3、4点。
它还有一种
反正我看他那个字，
我有点想去了，它这种 action 可以像做一个 operator。
这主要是但是不知道也不知道3点才来就往在意。
OK， 那我就是
大的一个
要讲东西多嘛。
还有像我主要是讨论一个 model space integration，
我们刚刚做了它，然后下一步变成线。
他现在
就是测出来一大堆结果，让他看一下。
对不对？
也不是对不对，就是有什么样的。
现在就是他好像可以
这个对不对，肯定我能
搞一个
断出来是对
换是 function，
我看这玩意儿测出来是什么意思，然后
定
到太久，有人主要是给他展示结果。
model space integration 就是一个 configuration space integration， 就这种东西，就是说是把三个点放在这个。比如说现在 disk， 你就说 disk， 就把3个点放在 disk 上，然后做某种东西的积分。这是哪3个点？它现在有2种点，一种是边界上的点，一种是内部的点。对，它现在就是你把这些点所有的位置所有的点的位置全部都给它击掉。